BIDS validator doesn't mean necessarily it's fully feature complete. The validator is a little bit permissive sometimes in what can be there. So it'd be nice if when you had a data set I ended up kind of curating it a little bit for them. You add these channels.tsv or this events.tsv. So in this subject 0, you have a coordinate system.json, which is going to tell you that it's in cap track with meters, units, and you have an electrodes that they included, but then you can also have a channels, which is helpful because it tells you that the status is good and that they're EOG channels at the bottom. So since they didn't include those, it doesn't work automatically with these automated tools to read in bids. So it's really helpful to have all these things. So the first thing is I'm not actually going to run this bottom one, but it's this last command here is an automated one that will download off of OpenNeuro the whole data set for you, and so it's kind of nice. Then you can do it all in code. You don't have to unzip the file or anything like that. So this scales well. So if you want to do 4 data sets or 5 data sets, you can just write the code to access these data sets. And then I was looking at their montage, and their montage was a little bit confusing too. So it's a biosemi montage, but they have some interesting channels in there. And this is where I was saying those sidecars are really helpful because if you just read the raw file, so then the channel names are things like D1, D2, D3, D4, but then when they include the channels, they rename them to things like CZ, CP1, C1, the kind of more informative about the position of the channels rather than just counting them. So I fixed some of the things about putting these sidecars in, so it included a little bit of code. So then the next step I generally do with the data set is to find, you can look for all these extensions that are data files that are EEG data files. EDF or VHDR, BDF are usually what EEG data files will be. And so then if you just look at the bids paths, there's 86 of them, and it should be 2 per subject. There's 42 subjects, and then or 43 subjects, and then because it starts on 0, and then each subject is both a responder and a something else. They're a responder and they're an ultimatum game and a responder and a proposer. So there's a responder part of this ultimatum game and a proposer part. So you could separate those out based on which the task is. So you can see, it's got a proposer. So if the task is proposer, then you could also find matching paths with task equals proposer or task equals responder to separate those out. And then the next part is loading in the data and plotting a PSD, which I showed kind of in the pre-processing steps. And yeah, usually when you load in, there's like a lot of verbosity about things not working or things going on under the hood with the channels being set, but everything went well with this. You have a nice channel positions, and you can see the power spectral densities here. Those all look pretty good. Like I was saying, you get this kind of 1/f, and then you get some kind of alpha, beta, delta peaks. This is the line noise. And Biosemi does a really good job having very little line noise, which is helpful. So power spectral density is a really great part to start to make sure that the data is clean and there doesn't need to be channels removed. So if there is a channel that needs to be removed, usually it'll show up in the power spectral density somewhere, and then you can remove it in the channels part of the bids data set. This channels one tells you if the status is good or bad, and so then once you do that once, then everyone else who downloads the data set will have the appropriately marked channels as good or bad. And so then I just did this global rejection threshold, like I was mentioning, so that when we do the ICA, it's filtered, and then there's not large artifacts and movements So we can make some temporary epochs that are just fixed length epochs, so like just 2 seconds each, so that the epochs can get dropped where they were moving and grossly affecting the channel, so that that doesn't go into ICA, since those will just get rejected. Then, kind of following along with the slides, you want to take any channel that's causing most of these to be dropped, most of the drop logs, or most of the epochs to be dropped, and just mark it for interpolation. And so this is then what Dr. Sheen was saying about, well, so now you have your raw data, you have your epochs. These aren't really your epochs because you want to do them based on based on like an event instead of just fixed length epochs, like segmenting them. But if you want to get just the data, you can do raw.get data, and this will return it as a NumPy array. So then you have it based on the shape and the number of samples, so that there's your raw data. And so then we can set them to average reference and fit an ICA. This isn't maybe the best subject as an example because they don't have a ton of bad channels or blinks in there. Like they had a kind of strangely few number of blinks in this case. So the ICA does take like a couple minutes to finish. Maybe I'll pause there while the ICA is going. Any questions? Or is that helpful?
Yes. Dr. Alex, I have a question to confirm. We are doing these steps for each patient, for each separate patient. Okay, then we are repeating this for each patient in our cohort.
Yeah, you'd want to loop over all the bids passed to do it for every patient.
Okay, it's very clear.
Yeah, so if you wanted to do these again, or if you have a really good deep learning algorithm that doesn't need preprocessing, you could just get the arrays out from the raw data. But again, it's probably a good idea just to check with preprocessing that you get similar results and that your deep learning algorithm isn't learning something that's non-neural. But yeah, you could just get the raw arrays from that.
Yes. Also, Dr. Alex, do you suggest a package or something to combine all the patient together? If I want to combine all the data together to be used in one model, deep learning model, for example.
Yeah, so if you focus on deep learning specifically, you probably want you can combine them all in an array, but if each subject is 1 gigabyte's worth of data and you have 43 subjects, you're not going to have a computer that can store 80 gigabytes of data in memory. So then you could save them to like a NumPy array and do lazy loading and just pull each of them up at a time. That's one method. There's work in M&E to get them saved in these EDF, BDF file formats. FIF is another file format, but less work has been done to do lazy loading for those. So they tend to require more RAM.
Okay, it's very clear. Thank you.
Yeah, so just NumPy for that. I don't think you need anything else.
Okay, so you suggest to convert them each patient to NumPy arrays and combine NumPy arrays. It will be much efficient, computer efficient.
Yeah, so as far as computer efficiency, you could take all of the data out in NumPy arrays, or you could process them. You could load them on a disk only when you need them. Probably efficiency-wise would be the best way to do that. And so you could just either load them and then delete them. Save them to a NumPy array, or save them to a FIF file and then load them, and then when you're done with them, delete them.
Sounds great. So the ICA still working in the background.
Oh yeah, it's finished. And it does tell you how long it took, 97 seconds. So yeah, and then I will say another thing about just using deep learning about non-processed data is that like you get epochs that are rejected because the person was moving and created some large artifact on the data. And so if you just use deep learning, that's probably going to be one where it fails, and so that's going to reduce the accuracy of your metric because it's failed because the data is not really neural data, it's just noise on that one. So even though the algorithm, it's not going to bias the success of the algorithm, it will reduce your results so that it looks like your model is not performing as well as it should be performing, because you should only count the model on actual data from the brain. So then, like I was saying, these are the automated algorithms to find. So you can just pass in the data object, and you can find which ones look like muscle. And in this case, there's not much muscle, so nothing got marked. It would be red if it was marked. And then you can also look for ones that have blinks. And I think this one, oh, there's still no blinks. All of them were pretty low. So this data was already pretty clean, and we didn't need to apply and remove any ICA components anyway. So it's pretty minimal, but this scales really well in case you want to run on 43 subjects without a lot of manual input. It takes a lot of time to do all that. And so then finally, this is the slide I was talking about, running auto reject. You can reject. You can make some epochs that you actually want to analyze. The other ones were just temporary. And you can pick an event. In this case, I picked 64 and a reasonable time interval and make some epochs. And this is what's actually going to be your data. And this would be like what you could feed into a deep learning algorithm, where you have not just the raw data, but you have events, and you want to classify, and you want to do a test training split and see if you can classify successfully each of the events as whichever one. So if I had event ID 64, and then I also made epochs with event ID 192, I think that's what is in this data set, then and you can look at the events that are in this event ID data structure, then it'll tell you which events are in your data set. I mean, if you've made the data set and you're not getting it off the internet, then you should know which events you've triggered. But if we just pick an event to study, and then we could try and classify it based on compared to another event, and use deep learning, use classical machine learning, use classical statistics to figure out which features of the time course or which features of the time frequency decomposition are important for classifying, or just build a really good model if the application is much more that the algorithm just needs to work, like a brain computer interface or something. Maybe you don't care so much which frequencies and which times, and that's also a trade-off of using deep learning versus more classical machine learning versus classical statistics, is trying to understand the neural basis of your classifications, the neural basis of the difference, versus just having something that performs. And so for the deep learning, like for instance, the big Nature paper by Dr. Chang and ECSF's group is using deep learning to decode from ECOG actual speech, and so the brain activity is converted via deep learning to something that sounds mostly like human speech. And so in that case, it's not as essential, which parts of the brain and which frequencies and what the time course looks like for those channels, as much as it is that the algorithm makes realistic speech. And so that's a great application of deep learning, versus if you want to know more about which time frequencies are involved in speech, perhaps you'd want to use something like classical statistics or classical machine learning to have something a little bit more interpretable. And then lastly, I had this fix, but then you're basically done, besides converting to source space as well. I don't want to just keep talking. I feel like this code is something that somebody could walk through, and this would be a good place to start for pre-processing EEG data. And I'm happy to share it, but I thought maybe maybe there aren't any more questions, and I'm happy to talk more about applications of deep learning if that's where this group has most of their interest.
Yes. Can I share my screen to show you some of my codes? I'm stopping the recording now.